we've looked at the Carnot cycle thermodynamically. Now, back then, the engineers were interested in efficiency, how to get the most bang for the buck, so to speak. So they defined efficiency of an engine, or a heat engine in particular, as the energy you get out divided by the energy you put in. And if the energy, or if you have a 100% efficient engine, then all the energy you put in is equal to the energy that the machine does, the engine does. So the efficiency of 1 will mean all the energy in, you get all the energy out as work. The efficiency of a Carnot heat engine that we're talking about, let's define that as the work we get out of the engine divided by the heat we put in the engine. Now, there's no reason why, from the first law, that this efficiency cannot be equal to 1. But what we'll find is that never ever in human experience has one been able to completely get 100% of the work out for the heat you put in. If you put 100 joules in, nobody ever has seen that you'll get 100 joules of work out of a heat engine. From experience, we find that we never can make a 100% efficient heat engine, even though it is consistent with the first law, so therefore there must be a second law of thermodynamics. And again, this comes from our experience, our collective human experience. We never have been able to 100% convert heat into work. So we need a second law. Right, so let's see if we can get this expression for the efficiency of a heat engine. We're going to define the efficiency of a Carnot engine as the work we get out over the heat we put in. So the work we put in, we're going to have to use a minus W total. I'll explain that in just a second. And the heat we put in on the Carnot cycle is that heat we put in on that first step, when we transfer some heat from the hot temperature reservoir into the engine. So why this minus? Remember, engineers are interested in the work you can get out of a system. So they're interested in, like if you do 100 joules of work, they want that to be a positive number. But the way we set up our sign convention is that if the engine does work on the surroundings, then that's a negative number, because the engine, the system, is losing energy to the surroundings. So we're going to put a negative sign here in order to make this a positive number, so that our efficiency can be a positive number. And the heat we put in, the system, the engine is gaining energy, so that'll be a positive number. So this will be a positive number. That's why that negative sign is there. Let's see how much energy we put in. Oh, look. Minus W total is Q1 plus Q3. All right, the heat transferred in these, for the isothermal steps, the adiabatic steps, there's none. So that's the total heat put in, or sorry, the total work done is equal to Q1 plus Q3. This is equal to the minus the total work. So this is equal to Q1 plus Q3 over Q1. Just divide each thing by Q1. This is 1 plus Q3 over Q1. So there's the efficiency of a Carnot heat engine. It's just the heat you put in at the first step divided by, or sorry, goes into, divided into the heat that comes out on the third step. And we know that the heat, we just said, we argued that in fact this absolute number is greater than that one. And we also argued that this is a number greater than 0, but Q3, remember, is less than 0, and Q1 is greater than 0. So this means that Q3 over Q1 is less than 0, which implies that the efficiency is 1 plus a negative number. So the efficiency will always be less unless you can have Q3 equal to 0 or Q1 equal to infinity. That's usually not the case. So you can't transfer an infinite amount of heat into the system. That will make that efficiency 1. Or you can't suck out, or you can't have no heat come out of the system. Q3 can't be 0. This implies then efficiency is less than 1. All right, so you can't get a 100% efficient heat engine. Now, so we've shown that. Let's get another form for the efficiency of a heat engine. where this is the temperature of the low temperature reservoir, the temperature of the high temperature reservoir. All right, so we'll just again analyze this thermodynamically. In step 1, which was isothermal, we can say that the heat transferred in that step 1, Q1, will be equal to minus W1. Remember, isothermal, delta U is equal to 0, so Q is equal to minus W. So that first step, Q is minus W, and the work is just minus nRT, natural log. Let's use VB over VA as the volume at stage B divided by the volume at stage A. Here we are. We're starting up here, stage A. We'll go to B isothermally. We'll go to C adiabatically. We'll go to D isothermally. We'll go back to A adiabatically. So this is a isothermal expansion, and let's assume that we have an ideal gas. Assume ideal gas. All right, so there is the heat transferred, work done, isothermal compression. And what is this? This is the temperature of the high temperature reservoir, TH. Let's look at step 3. Step 3, again, that's an isothermal. So we can use the exact same argument. Q3 will be minus the work done in step 3. And that's minus nRT. But remember, in step 3, we have heat flowing in the low temperature reservoir times the natural log of VD over VC. All right, so this was the isothermal expand or contraction. Actually, we're compressing the gas in step 3. We said that's that. And let me just define what D and C are here. So we have up here. So we have volume A, volume B, volume C, and volume D. So this is isothermal. Step 3 is isothermal. So going from C to D, the final volume is the volume at D minus the initial volume at C. So that's where that comes from. Now, let's look at the adiabatic steps. Now remember, in step 2, that's adiabatic. Remember, I probably from lecture 3 or maybe lecture 4, for an adiabatic compression of a gas, the final temperature over the initial temperature is equal to the final volume over the initial volume raised to this 1 minus gamma, where gamma is ratio of heat capacities, Cp to Cv. So let's apply that to step 2, the adiabatic expansion. Now in step 2, maybe just touch base here. Start. All right, so there's the isothermal, and we're right down here. Now we're going to switch to adiabatic. So we're starting at a high temperature. That was the temperature. The gas was initially the temperature at the high temperature reservoir, 600. Now and it's at volume VB. And then finally, the gas down here, after the adiabatic expansion, the temperature is at the temperature of the low temperature reservoir at volume VC. And there's a low temperature reservoir right there. So for that second step, adiabatic step here, we have a final volume of VC and a final temperature of the low temperature gas, and the initial temperature was the temperature, high temperature reservoir, and volume VB. That's where this is. So the final temperature is the temperature of the low. Initial temperature was temperature of the high, and that's equal to the final volume, which was, we said, the volume at stage C divided by the volume at stage B raised to the 1 minus gamma power. We do the same analysis for step 4, which is adiabatic. We find, well, in step 4, might as well go back up here. So here comes step 3. Got heat flowing. Keep going there. Now the gas is at the temperature, the low temperature reservoir. That's the initial temperature in volume VD, point D. And now at the end of that adiabatic expansion, we have the temperature of the gas to be the temperature of the high temperature reservoir, and the volume being VA. So that's the initial is down here. So with that, the final temperature is the temperature of the high temperature reservoir. Initially we started at low temperature, and the final volume was the volume at A, and the initial volume we started at point D. And again, this is raised to the 1 minus gamma power. So it looks like so where are we going here? Well, just so we don't lose sight here, what we want to do is to convert. So we derive this expression. Now we want to know something about how efficiency depends upon temperature of high and low temperature reservoirs. All right, so somehow we have to get rid of the Q's and replace them by T's. Look, here's some T's there. There are some Q's. If we can relate VA, VB, VD, VC, take the ratio. There's how we can get a relationship. So let's rearrange. What should we do here? Let's do this one. All right, so let's rearrange this. Let's say this T low over T high. That's equal to VD over VA raised to the 1 minus gamma power. So we have an expression for low to high in terms of VC and VB, and low to high in terms of VD and VA. So let's equate those two. So we can say that VC over VB raised to the 1 minus gamma power, that's equal to D to A raised to the 1 minus gamma power. Well, we just take this root 1 minus gamma, so this implies that VC over VB is equal to VD over VA, or in other words, VC over VD is equal to VB over VA. Well, that's useful. Let's take this ratio, Q1. Actually, what do we want here? We want Q3 to Q1. So let's say Q3 to Q1. So Q3 to Q1, that's equal to nRT, this is T of the low temperature, times the natural log of VB over VA, sorry, VD over VC, minus give us a plus, VD over VC, over nRT times, that's T, the high temperature reservoir. Q1 was a high temperature reservoir, times the natural log of V, just get this right here, VB over VA. Oh, look, things start canceling out here. That goes away. We have that ratio, which is what we wanted here, low to high, but these things don't cancel out. But, look at this. So, oh yeah. So let's, what do you want to substitute in? Take a poll, substitute in for B over A. Yeah, let's do that. This is equal to T low over T high, natural log of VD over VC, natural log of VC over VD, almost there. That's equal to T low over T high, natural log of VD over VC divided by the natural log of VD over VC with a minus sign in it. Because remember, you switch these, change the minus, times the minus 1. So it's equal to just minus T low over T high. So the ratio of Q3 to Q1 is minus T low over T high. So 1 plus Q3 over Q1 is equal, and that's what the efficiency is equal to 1 minus T low over T high. All right, so that's what we set out to prove here, 1 minus T low over T high. So this means to get the efficiency equal to 1, what do you have to have? This implies that T low has to equal 0, or T high has to equal infinity. Now, we've never ever seen an efficient, 100% efficient engine where you can convert 100% of the heat you put into an engine into work. So this means that you can never have T equals 0. In other words, T, this in Kelvin, never have absolute 0. And you can never have an infinitely high temperature. So this means the efficiency is E never equal to 1. This is also interesting is that if you increase the difference in temperature between the low and high temperature reservoirs, then you'll have an increase in efficiency. As, for instance, suppose you have this is 100 degrees, 100 Kelvin, and make this a 200 Kelvin. If this engine, you have an efficiency 0.5. Now, if you say make this a higher temperature, say put this to 300 Kelvin, then the efficiency goes to 0.66. So as you start increasing the temperature of the high temperature reservoir or lowering the temperature of the low temperature reservoir, you start increasing the efficiency of the engine. The hotter you can make that heat engine run, the more efficient the heat engine will be. Of course, this is all frictionless reversible processes, so this gives the maximum. That's another interesting point, is that even though we have the best heat engine, in other words, frictionless and reversible, E can never equal 1. There's a fundamental limit on the efficiency you can get out of a heat engine, and that fundamental limit is called the second law of thermodynamics. I think we just had one more point here. Efficiency is 1 plus heat out over heat in, and that's equal to 1 minus T low over T high. These two things are equated so that Q3 over Q1 plus, we'll just put that out, get rid of the ones and so on, plus T low over T high, that's equal to 0. Or in other words, let's multiply both sides of this equation by Q1 over T low. We'll have Q1 divided by T high plus Q3 divided by T low equal 0. Well, what does this mean? This means if you go through a cycle, this is how much heat you put in the entire cycle. This is the first step and the third step, and the second and fourth were adiabatic, so mean no heat transferred. This is the total heat put in. That depends on path. But if you divide by the temperature of the reservoir, so this is the first step divided by the temperature you had of the reservoir of the first step, and the heat in the third step divided by the temperature you had of the third step, you sum those through that cycle, it's equal to 0. So this implies that Q over T is some sort of, if you add things and you get 0, some sort of state function. Okay, that's cool. And maybe remember from introductory chemistry, entropy defined as Q over T for a reversible process is a state function. All right, so that's just where we're going in the next part of this lecture. And finally, based on thermodynamic efficiency, explain why it is better to run a steam engine with superheated steam, which is hotter than 100 degrees, than with steam at 100 degrees, and make the bad assumption that a steam engine is similar to a Carnot heat engine. All right, well, we just already answered that question here. The idea here is if you have the high temperature reservoir, the higher temperature you can make that high temperature reservoir, the smaller this number will be, and the smaller number you'll be subtracting from 1, and the better efficiency you'll have, efficiency closer to 1. If this goes up, this term goes down, you're subtracting a smaller number from 1, you get a higher efficiency. All right, so that's it for this part of lecture 4.